Have you ever noticed how things around you are rarely still? Think about it for a moment. The sun moves across the sky, even though it feels like we are the ones moving. A plant in your window slowly grows taller, reaching for the sunlight day by day. If you pour hot chocolate into a mug, it doesn't stay piping hot forever. It gradually cools down. Even when you're sitting perfectly still, your heart is beating, and you are breathing. Change is happening all the time. Everywhere we look, in big ways and in tiny, almost unnoticeable ways. It's a fundamental part of how our universe works, from the smallest particles to the largest galaxies. In mathematics, we love to understand patterns and describe how things work. So it's no surprise that mathematicians became very interested in understanding change itself. How can we measure change? How can we predict how something will change in the future based on how it's changing right now? These are big questions. It's not just about saying something is changing, but about describing how fast it's changing, and whether that rate of change is itself changing. This might sound a little complicated at first, but it's a truly fascinating idea that opens up a whole new way of looking at the world through the lens of mathematics. Think about a journey. If you travel from one city to another, your position is constantly changing. Sometimes you might be going fast on a highway, and other times you might be stuck in traffic, moving very slowly. Understanding these changes in speed, and how speed itself changes, that's acceleration, is crucial for planning your trip and understanding the journey. Mathematics gives us the tools to analyze these kinds of dynamic situations with precision. Instead of just having a general idea, we can get specific numbers and make accurate predictions. This is where the exciting field of calculus comes into play, providing us with powerful methods. Calculus is often described as the mathematics of change, and one of its most fundamental concepts is something called a derivative. The derivative is like a special magnifying glass that allows us to zoom in on any moment of change and understand exactly what's happening. It helps us measure instantaneous rates of change. Don't worry if these terms sound a bit technical right now. We're going to explore them together, step by step, using simple examples. You'll see that the core idea is actually quite intuitive and incredibly useful for making sense of our ever-changing world. Get ready to unlock some math magic. So what exactly is this thing called a derivative? In the simplest terms, a derivative measures how a function changes as its input changes. Think of it as a way to find the rate of change of something at a very specific instant. Imagine you're driving a car. Your car's speedometer tells you your speed at any given moment. If it says 60 miles per hour, that's your instantaneous speed. It's not your average speed over the whole trip, but your speed right now. A derivative is like a mathematical speedometer for functions. It tells us how fast the output of a function is changing at a particular point of its input. Let's consider a function as a relationship between two quantities. For example, a function might describe how the distance you've traveled changes over time. If you plot this relationship on a graph, with time on one axis and distance on the other, you'll likely get a curve. If you're traveling at a constant speed, this graph will be a straight line. But what if your speed is changing? What if you're accelerating or slowing down? Then the graph will be a curve. The derivative helps us find the slope or steepness of that curve at any single point along it. This slope represents the instantaneous rate of change. Why is the slope important? Well, the slope tells us how quickly one variable is changing with respect to another. If the slope is steep, it means the function's value is changing rapidly. If the slope is gentle or flat, it means the function's value is changing slowly, or perhaps not at all at that specific point. For our distance time graph, a steep slope means you're covering a lot of distance in a small amount of time. You are going fast. A gentle slope means you are covering less distance in the same amount of time. You are going slower. And a flat slope, a slope of 0, would mean you are not moving at all at that instant. So, a derivative isn't just some abstract mathematical number, it gives us crucial information about behavior. It quantifies how sensitive a function's output is to tiny changes in its input. It's like asking, if I nudge the input just a tiny bit, how much will the output jump or fall? This concept of instantaneous rate of change is incredibly powerful, because many things in the real world don't change at a constant rate. They speed up, slow down, peak, or bottom out. Derivatives give us the tools to analyze and understand these dynamic behaviors with remarkable precision, which is why they are so fundamental in calculus and its applications. To really understand what a derivative is showing us, it's helpful to visualize it on a graph. Imagine we have a curve representing our function, say, the path of a ball thrown into the air. At any point on this curve, we can draw a special line called a tangent line. A tangent line is a straight line that just touches the curve at that single point without crossing through it right there. Think of it like a ruler, carefully balanced on the edge of a curved shape. It matches the direction of the curve at that precise spot. This line is incredibly important for understanding derivatives. The slope of this tangent line is precisely what the derivative of the function is at that point. Remember, the slope of a straight line tells us how steep it is, its rise over run. So if the tangent line at a certain point on our curve is very steep, it means the function is changing rapidly at that point. If the tangent line is almost flat, it means the function is changing very slowly, or perhaps not at all at that specific location. The derivative, therefore, gives us the value of the slope of this unique tangent line at any chosen point on our function's graph. Why is this instantaneous idea so important? Let's go back to our thrown ball. Its speed isn't constant. It's fastest when it leaves the hand, slows down as it goes up, momentarily stops at its peak, and then speeds up as it comes down. If we wanted to know its speed exactly 1 second after being thrown, we couldn't just use an average speed. We'd need its speed at that precise instant. The derivative, by giving us the slope of the tangent line to the path of the ball, plotted as height versus time, at tt equals 1 second, tells us exactly that instantaneous speed. It captures the rate of change at that fleeting moment. This concept of a tangent line representing the instantaneous rate of change is a cornerstone of differential calculus. Before calculus, mathematicians could easily find the slope of a straight line. However, finding the slope of a curve at a specific point was a much harder problem. The brilliant insight of Isaac Newton and Gottfried Wilhelm Leibniz, who independently developed calculus, was to define this instantaneous slope using the idea of limits, essentially looking at slopes of lines that get closer and closer to the tangent. The derivative is the result of this powerful idea, giving us a way to precisely quantify change at any given instant. Now that we have a feel for what a derivative is, an instantaneous rate of change or the slope of a tangent line, let's explore where this math magic shows up in our everyday lives. You might be surprised how often the principles of derivatives are at play, even if we don't consciously think about them in mathematical terms. One of the most common examples, as we've touched upon, is driving a car. Your speedometer is essentially displaying a derivative, the rate of change of distance with respect to time, which is your instantaneous speed. When you press the accelerator, you're changing that rate. Think about something as simple as a plant growing in your garden or on your windowsill. It doesn't just instantly appear at its full height. It grows over time, little by little. The rate at which it grows might change depending on the amount of sunlight, water, or nutrients it receives. If you were to measure its height every day and plot it on a graph, the derivative at any point on that graph would tell you how fast the plant was growing at that specific moment in time. A biologist might be very interested in this to understand optimal growing conditions. Consider a cup of hot coffee or tea. When you first pour it, it's very hot, but over time it cools down, losing heat to the surrounding air. The rate at which it cools is not constant. It cools faster when it's much hotter than the room, and slows its cooling as it gets closer to room temperature. This is described by Newton's law of cooling, which involves derivatives. The derivative would tell you how many degrees Celsius the coffee's temperature is dropping per minute at any given moment. This understanding is crucial in fields like food science and engineering. Even when you're filling up a swimming pool, derivatives are subtly at work. If the pool has a complex shape, the rate at which the water level rises might not be constant, even if the water is flowing in at a steady rate from the hose. For instance, if the pool gets wider as it gets deeper, the water level will rise more slowly as it fills up. A derivative could tell you exactly how fast the water level is rising at any particular depth. These examples show that understanding rates of change is fundamental to describing and predicting how countless everyday processes unfold around us. The applications of derivatives extend far beyond simple everyday observations into the core of many scientific and analytical fields. In physics, derivatives are absolutely fundamental. We've already talked about speed, or velocity, being the derivative of position with respect to time. But it doesn't stop there. What about acceleration? Acceleration is the rate at which your velocity changes. So, acceleration is the derivative of velocity with respect to time. If you're pressing the gas pedal in a car, you're accelerating, meaning your velocity is increasing, and this rate of increase is what acceleration measures. Think about the forces acting on objects. Newton's second law of motion, force equals mass times acceleration, directly involves acceleration, which, as we just saw, is a derivative. This means that to understand how forces cause motion, physicists rely heavily on calculus and derivatives. From calculating the trajectory of a rocket heading to Mars to understanding the vibrations in a bridge structure, derivatives are essential tools for modeling the physical world. They help engineers design safer cars, taller buildings, and more efficient engines by allowing them to precisely analyze how things move and change under various influences. Derivatives are also incredibly powerful in the world of economics and business. Economists often talk about marginal concepts. For example, marginal cost is the change in total cost that arises when the quantity produced is incremented by 1 unit. Essentially, it's the derivative of the total cost function with respect to the quantity produced. Knowing the marginal cost helps a company decide whether it's profitable to produce one more item. Similarly, marginal revenue is the additional revenue generated by selling one more unit, which is the derivative of the total revenue function. Businesses use these derivative-based concepts to maximize profits and make strategic decisions. Beyond physics and economics, derivatives pop up in chemistry to study reaction rates, in biology to model population growth or the spread of diseases, in computer graphics to create smooth curves and surfaces, and even in finance to assess risk and price complex financial instruments. The list is truly extensive. Whenever a system involves quantities that are changing, and we want to understand the precise nature of that change at specific moments or under specific conditions, derivatives provide an indispensable mathematical framework. They empower us to move from simply observing change to quantifying, predicting, and even controlling it. Now that we've seen how incredibly useful derivatives are, you might be wondering, how do we actually find them? While the formal definition involves limits, mathematicians have developed shortcut rules for finding derivatives of common functions. One of the most fundamental rules is called the power rule. It's a real workhorse for functions with variables raised to a power, like x squared or x cubed. The power rule is wonderfully straightforward. Say you have f of x equals x to the n, wherein is the exponent. To find the derivative, you do two simple things. First, bring the exponent down in front and multiply it by x. Second, reduce the original exponent by 1. So, the derivative of x to the n is n times x to the n minus 1. Let's break that down. Step 1. Identify the exponent. In x to the fifth, the exponent is 5. Step 2. Bring that exponent to the front. So, we'd have 5 times something. Step 3. Keep the variable x as it is. Step 4. Reduce the exponent by 1. For x to the fifth, the new exponent becomes 4. Putting it all together, the derivative of x to the fifth is 5x to the fourth. Once you see the pattern, it becomes easy to apply. This rule is incredibly efficient. Imagine finding the slope of x to the 100th by drawing tangent lines. Practically impossible, but with the power rule, we find its derivative in seconds. The derivative is 100x to the 99th. Isn't that neat? This rule simplifies complex concepts into simple algebraic manipulation. It's one of the first major shortcuts that makes calculus powerful and practical. Let's solidify our understanding of the power rule with a couple of clear step-by-step examples. This will help you see just how easy it can be to find a derivative once you know the rule. Suppose we have the function f of x equals x squared. This is a very common function. Its graph is a parabola, a U-shape. We want to find its derivative, f prime of x, which will tell us the slope of this parabola at any point x. According to the power rule, f of x equals x to the n becomes f prime of x equals n times x to the n minus 1. In our case, x squared means n equals 2. First, we identify the exponent n. For f of x equals x squared, the exponent n is 2. Step 2 of the power rule says to bring this exponent down in front of the x, so we'll have 2 times x. Step 3 says to reduce the original exponent by 1. Our original exponent was 2, so the new exponent will be 2 minus 1, which is 1. Therefore, the derivative f prime of x is 2x to the 1. Now, anything raised to the power of 1 is just itself. So x to the 1 is just x. So the derivative of f of x equals x squared is simply f prime of x equals 2x. This means the slope of the parabola y equals x squared at any point x is given by 2x. Let's try another one. What if our function is f of x equals x cubed? Here, the exponent n is 3, following the power rule. First, bring the exponent 3 down to the front. This gives us 3x. Second, reduce the exponent by 1. The new exponent will be 3 minus 1, which is 2. So, the derivative of f of x equals x cubed is f prime of x equals 3x squared. This tells us that the slope of the curve y equals x cubed at any point x is given by the formula 3x squared. For instance, at x equals 1, the slope is 3 times 1 squared, which is 3. At x equals 2, the slope is 3 times 2 squared, which is 3 times 4, or 12. The curve is getting steeper. What if there's a number already multiplying our x term, like f of x equals 5x squared? This is where another simple rule comes in, the constant multiple rule. It says that the derivative of a constant times a function is the constant times the derivative of the function. So, for 5x squared, we can just keep the 5 aside, find the derivative of x squared, which we know is 2x, and then multiply them. 5 times 2x is 10x. So, the derivative of f of x equals 5x squared is f prime of x equals 10x. These basic rules, especially the power rule, are the building blocks for differentiating more complex functions later on. Practice them, and they'll become second nature. We've mastered the power rule, which is fantastic for functions like x to the n. But what about even simpler functions? For instance, what is the derivative of a constant number like f of x equals 7? A constant function, when graphed, is just a horizontal line. Think about it. If f of x equals 7, it means that no matter what value x takes, y is always 7. The line y equals 7 has no steepness at all. It's perfectly flat. And what's the slope of a perfectly flat horizontal line? It's 0. So the derivative of any constant is always 0. This makes intuitive sense. If something isn't changing, its rate of change is 0. So if f of x equals c, where c is any constant number, then its derivative f prime of x is 0. Whether c is 5, -10, or a million, its derivative is 0. This is a very important and simple rule to remember. It applies to any number that isn't attached to a variable that's changing. This rule works hand in hand with the power rule and other derivative rules. For example, if you had a function that was just a number, say g of x equals 10, its rate of change is 0 because it never changes value, so g prime of x is 0. This is a foundational piece of our derivative toolkit. Another incredibly useful rule is the sum or difference rule. This rule says that the derivative of a sum of functions is the sum of their derivatives. Similarly, the derivative of a difference of functions is the difference of their derivatives. In simpler terms, if you have a function that's made up of several parts added or subtracted together, you can find the derivative of each part separately, and then just add or subtract those results. This is super helpful because it allows us to break down more complicated-looking functions into smaller, manageable pieces that we already know how to differentiate. For example, let's say we have the function h of x equals x squared plus x cubed. We already know how to find the derivative of x squared, which is 2x, and the derivative of x cubed, which is 3x squared. Thanks to the sum rule, the derivative of h of x is just the derivative of x squared plus the derivative of x cubed. So, h prime of x is 2x plus 3x squared. Isn't that convenient? We don't have to do anything fancy. We just differentiate term by term. If it was h of x equals x cubed minus x squared, then h prime of x would be 3x squared minus 2x. These rules, derivative of a constant power rule, constant multiple rule, and sum or difference rule, form the basic machinery for differentiating many polynomial functions. So, we've taken a journey into the world of derivatives, starting with the simple idea of change and seeing how mathematics gives us a precise way to measure it. We've learned that a derivative is essentially the instantaneous rate of change of a function, or the slope of the tangent line to its graph at a specific point. It's like a speedometer for mathematical functions, telling us how fast things are changing at any given moment. This concept, while sounding a bit abstract at first, unlocks a powerful way to analyze and understand the world around us, which is constantly in motion and transformation. We saw that derivatives are not just confined to textbook problems. They appear everywhere in real life. From the speed of a car and the acceleration of a rocket, to the growth of a plant, the cooling of coffee, the fluctuations in economic markets, and the rates of chemical reactions, derivatives help us model and quantify these dynamic processes. They allow physicists, engineers, economists, biologists, and many other professionals to make predictions, optimize systems, and gain deeper insights into how things work. The ability to understand rates of change is truly fundamental. We also dipped our toes into how to actually find derivatives, focusing on some basic but very powerful rules like the power rule, the derivative of a constant, and the sum or difference rule. These rules provide us with an algebraic toolkit to calculate derivatives without always having to go back to the more complex limit definition. With these tools, functions that describe curves and changing quantities become much more manageable, and we can extract valuable information about their behavior, where they are increasing, decreasing, or reaching peaks and valleys, simply by examining their derivatives. Ultimately, derivatives change the way we think about mathematics and its connection to the physical world. They bridge the gap between static descriptions and dynamic reality. They allow us to move beyond simply stating that things change, to precisely quantifying how they change. This capability is at the heart of calculus and has revolutionized science, engineering, and many other fields. As you continue your mathematical journey, you'll find that derivatives are a foundational concept that opens up even more advanced and fascinating areas of study, all aimed at understanding our wonderfully dynamic universe. Keep exploring and keep asking how fast.